So good afternoon. My name is Hanuka from Technion, and our research focuses on a future coherent of X-ray source. We contemplate the system to be the seed for an advanced light source or as a compact medical X-ray source. In this talk, we're going to focus on the maximum gradient in the Bragg accelerator. First, we'll see the full Bragg system-based X-ray free electron laser. Then our focus will be the accelerating gradient, and we'll wrap up with some conclusions. So let us see an animation of the full system. The full system consists of two Bragg waveguides. First serves as an accelerator. At the N01 mode, co-propagating with the electrons. They are injected from an optical injector, they accelerated, and then transported to the second Bragg waveguide. Serves as electromagnetic wiggler with a TEM mode, counter-propagating to the electron beam, wiggles them and generating the X-ray radiation. We ignore edge effects, and the transverse motion is ignored as well. These yellow dots you see, they're actually line charges. And once the laser, the accelerating laser and the line charges are inside the structure, the wake generated by the electrons decelerates the laser field. In order to compensate this deceleration, we must taper the laser, ensuring uniform gradient for all our line charges. Next, we are going to find the accelerating gradient, and in order to do that, we are going to formulate all these 5 things. So let us begin. The magnitude of the electric field increases from minimum on axis to maximum value on the discontinuity between the vacuum and the first layer. Then it decays exponentially through all layers, and from the maximum electric field, we extract the gradient. Next, we need to determine the maximum electric field. So the energy density is proportional to the dielectric coefficient of the first layer and to the electric field square. The energy flux is proportional to the energy density multiplied by the velocity, the energy velocity, which is proportional to the vacuum clearance. These two are the laser characteristics. Now, the maximum electric field sustained by the structure is limited by the fluence, which is the material characteristic, and it indicates the maximum field the structure may sustain before damage occurs. It equals to the pulse duration multiplied by the energy flux. Combining these 3 equations together, we extract the maximum electric field, which is proportional to the fluence and to the pulse duration, and of course to the vacuum clearance via the energy velocity. So what is the fluence? We used an empirical formula for fused silica developed in Livermore, California, and we see that it depends on the pulse duration, and its typical value is 2 joule per centimeter square for pulses shorter than 0.4 picoseconds. So we see the fluence dependence on the laser pulse. So we next need to understand what is the laser pulse, which is very important point. So we said all the electrons must experience a uniform gradient, but it must experience this gradient through whole time they traverse the structure. So assuming our electron beam is combined of M micro bunches separated by a laser wavelength, and assuming we have our laser. So since the laser propagates at the group velocity, while the electrons propagates virtually at the speed of light, it may happen that some of the electrons will not experience the laser field through whole time. In order to ensure that, we set a delay time between the first bunch and the laser pulse, such that the first bunch traverses the structure, it will experience the laser field through whole time. And second thing, we match the laser pulse duration to the macro bunch length, so that the last micro bunch will experience laser field through whole time. These two constraints are given. These two constraints are given in this formula, where the first term stands for the delay time, and second term stands for matching the macro bunch length to the laser. We're almost there. We see that the pulse duration depends on m number of micro bunches and on the half vacuum clearance. We still need to define the geometric length of our accelerator. This parameter is defined by final electron energy requirement, where gamma is the beam relativistic factor, and from Compton scattering we derive its value. For an example, for a laser wavelength of 1 micron and X-ray radiation at 1 angstrom, we get gamma 50. So at this point, we're done, and we notice that the accelerating gradient, the accelerating gradient depends on the maximum electric field, which in turn depends on the fluence. Both the fluence and the maximum electric field depends on the pulse duration, which in turn is determined by the geometric length. And this friend depends on the accelerating gradient itself. So this interdependence between these variables require a self-consistent solution, where our only two free parameters are m number of microbunches and the internal, which is the vacuum clearance. So here it is, the self-consistent solution. In this graph, we can see the gradient Vs half vacuum clearance. We can see for a single bunch and for m equals 10,000. We see that the gradient drops as the clearance gets wider. Thus, it's advantageous to operate with the smallest clearance as possible, leading to maximal gradient of less than half gigavolt per meter. If we compare the typical values of all the parameters we formulate before, we see that there is not much difference between single bunch and m equals 10,000 at the gradient value. And in order to illustrate this point, we have our second graph, where you can see the gradient depends on the number of microbunches for a quarter wavelength and for a 0.55 laser wavelength. The red line was multiplied by this factor such that both curves will coincide at m equals 1. We can see there is a critical value around m equal 1,000, and for values smaller than m equal 1,000, the gradient virtually independent of m, and for values greater than m equals 1,000, the gradient decreases a bit. So some conclusions. The accelerating gradient was evaluated self-consistently with the two free parameters, the internal and number of microbunches. We saw the critical value around m equal 1,000, leading to beam duration of 3.5 picoseconds. We saw that it's advantageous to operate with the smallest vacuum clearance as possible. Any novel acceleration concept intend to exceed the RF-based accelerators must demonstrate accelerating gradients greater than 1 gigavolt per meter. In order to get there, we need to replace our fused silica with a material which is typical value is 3.5 higher than the fluence we saw for the fused silica, assuming, of course, the same formula, the same empirical formula we saw. For the simulations not presented here shows it's better to use lower dielectric coefficient for the first layer. And for those of you who didn't have the chance to see our poster, I invite you at the next coffee break to visit our poster where we present the optimal number of electrons and maximum efficiency in the same Bragg accelerator. So these are my reference, and thank you very much.
Thank you very much also for finishing in time. So we have time for questions. Any questions? I have a question. If I understood right, you want to inject the electrons bunched?
Yeah.
What kind of bunches and how do you produce them?
So the optical injector we saw injects the electron bunched already in the modulate in the laser wavelength. At the same accelerating laser wavelength.
How do you do that?
Oh, this is a whole new story for another student. I'm dealing only with the accelerator and.
Okay. Okay, good. Thank you very much.
Thank you.